The debate over artificial sweeteners versus natural sugars often centers on weight control and blood sugar levels, but a deeper question is now gaining attention. How do these substances affect the brain's energy systems, particularly glycogen dynamics? Brain glycogen, primarily stored in astrocytes, is an underappreciated but critical reserve, regulating fuel availability during stress, learning, sleep, and neural activity surges. Disruptions in how glycogen is synthesized, stored, or mobilized can influence not only cognition but also long-term neurological resilience. As such, it becomes essential to explore how artificial and natural sweeteners, though similar in taste, might send profoundly different metabolic signals to the brain. Natural sugars like glucose and sucrose have well-mapped pathways in the central nervous system. When consumed, they elevate blood glucose levels, stimulate insulin release, and increase cerebral glucose uptake. In the brain, this readily available energy is either used directly by neurons or shuttled into astrocytic glycogen reserves via glucose transporters. This process is part of the brain's adaptive energy buffering system, particularly important during sleep, memory formation, and after intense neuronal firing. The dynamic turnover of glycogen in these contexts supports neuroplasticity, resilience to oxidative stress, and even mood regulation. In contrast, artificial sweeteners such as aspartame, sucralose, saccharin, or acesulfame K provide sweetness without caloric content and do not directly increase blood glucose. On the surface, this seems ideal for avoiding hyperglycemia and reducing dietary sugar load. However, their metabolic footprint on the brain may be more complex. While these compounds do not provide glucose to astrocytes, some can stimulate sweet taste receptors in the gut and pancreas, causing insulin release despite the absence of actual sugar, a phenomenon known as cephalic phase insulin response. This mismatch between sweetness and energy availability could have downstream consequences for glycogen dynamics. Specifically, insulin plays a role in regulating glycogen synthesis in the brain, not just in the periphery. If artificial sweeteners trigger insulin secretion but fail to deliver usable glucose to the brain, astrocytes may be signaled to store or manage glycogen without the necessary fuel, creating a form of metabolic confusion. Over time, such mismatches could impair the finely tuned energy buffering role of astrocytic glycogen, potentially leading to altered responses during cognitive tasks or emotional stress. Moreover, emerging studies in rodents suggest that chronic exposure to certain artificial sweeteners may impair glucose transport into the brain or alter the expression of key enzymes involved in glycogen metabolism. For instance, sucralose has been shown to modulate gut-brain signaling pathways that indirectly affect brain glucose sensing. Aspartame, which breaks down into phenylalanine and other metabolites, has been linked to changes in neurotransmitter balance and possibly oxidative stress, both of which can influence astrocyte function and energy management. Conversely, natural sugars, particularly in whole food sources like fruit, offer not just glucose but also fiber, polyphenol, and other micronutrients that modulate absorption and protect neurons from glycation and oxidative stress. These components may support healthy glycogen turnover by delivering slow, steady glucose alongside anti-inflammatory compounds. Thus, while refined sugars can certainly harm brain health when consumed in excess, their impact on glycogen metabolism may be more predictable and integrated than that of artificial sweeteners. Importantly, we still lack direct human data on how artificial sweeteners influence brain glycogen levels or turnover. Imaging techniques like 13C, MRS, magnetic resonance spectroscopy using carbon-labeled glucose, may one day help answer this question. For now, the field must rely on indirect markers, changes in cerebral insulin sensitivity, transporter expression, cognitive performance under metabolic stress, to infer how different sweeteners affect brain energy dynamics. From a practical standpoint, this growing uncertainty underscores the need for individualized dietary advice. For people with insulin resistance or diabetes, artificial sweeteners may offer short-term benefits in reducing glycemic load. However, if these compounds are found to impair the brain's ability to manage glycogen efficiently or induce misleading metabolic signals, their long-term impact could compromise cognitive performance, emotional stability, or even increase vulnerability to neurodegenerative conditions. In conclusion, artificial sweeteners and natural sugars may taste similar but operate along diverging neuroenergetic pathways. The brain does not merely respond to sweetness, it expects consistency between signal and substance. When that expectation is violated, as with non-caloric sweeteners, the consequences may ripple into the brain's foundational energy systems, including glycogen regulation. As we uncover more about how these compounds affect astrocyte neuron energy dynamics, the advice to simply swap sugar for sweeteners may prove to be too simplistic. Understanding the full neurometabolic cost and benefit of sweetness in all its forms is a crucial step toward protecting cognitive health in an increasingly artificial food landscape.